In the previous video, I introduced you to the idea of the mass flow rate. We can think of the mass flow rate as the rate at which fluid mass flows through some marked cross-section in a pipe. We saw in the previous video that if we have a fluid with density rho flowing through a pipe with cross-sectional area A at a flow speed V, then the mass flow rate, delta M over delta T, is equal to the density multiplied by the cross-sectional area of the pipe multiplied by the flow speed. In this video, we're going to use this formula for a quick example problem. Suppose that down here I have a beaker which holds a volume of 500 milliliters, and I'm filling that beaker with water using a pipe here. A nozzle has been attached to the end of the pipe, and the diameter of the nozzle is 2 millimeters. So let's say that we set this situation up, we turn on the water, and we find that the water fills the beaker in a time of 12 seconds. The question now, what is the speed at which the water is exiting the nozzle? We're going to solve this problem using the formula for the mass flow rate. I'll start by copying the formula over here. To start off with, we can ask, what is the fluid mass which fills the beaker in that time interval of 12 seconds? We know that the mass of a fluid is equal to the density multiplied by the volume occupied by the fluid. So let's just take this and substitute into the mass flow rate equation. We then have density times volume divided by the time it takes to fill the beaker equals the density of the fluid times area times flow speed. Notice in this equation that I have capital V and lowercase v. Capital V indicates the volume of the fluid when the beaker is full, and then the lowercase v indicates the speed at which the fluid is leaving the nozzle. Anyways, we can notice now that the fluid density cancels between the two sides. So I can now solve for the flow speed as volume divided by area divided by the time interval. Now the volume is given 500 milliliters. The time interval is given 12 seconds. So what area are we talking about? This area refers to the cross-sectional area of that stream which is coming out of the nozzle. How can we get the cross-sectional area of that stream of water coming out of the nozzle? Here I've drawn a figure which is supposed to illustrate that stream of water coming out of the nozzle. If we could take a slice through the stream, we would see that it has a circular cross-section, and that circular cross-section has diameter d, given by that 2 millimeters that I mentioned earlier. Now, how do I find the area of a circle using the diameter? Well, you're familiar with the formula that says that the area of a circle is equal to pi times the square of the radius. Now, the radius is half of the diameter, so I'll replace radius in the formula with diameter over 2. That gets squared. So that gives us that the area of a circle is pi times the square of the diameter divided by the square of 2, which would be 4. So I'm going to take this formula for the area in terms of the diameter and put it back into my equation here for the flow speed. Let's call the equations here 1 and 2. So I'm putting 2 into 1. That substitution gives me flow speed equals volume, then divided by area, pi diameter squared over 4, and divided by time interval. Now let's make the substitutions. So the volume is 500 milliliters. A milliliter is a cubic centimeter, so I'm going to put the volume in as 500 cubic centimeters. In the denominator, I have that pi over 4. Diameter is 2 millimeters. Since we already have something here in terms of centimeters, let's convert that diameter to centimeters. 2 millimeters would be 0.20 centimeters, and that gets squared. Then we have time, 12 seconds. Putting this into my calculator and rounding off to 3 significant digits, I get 1,330 as the numerical value. Now, as far as the units, notice that I have centimeters cubed over centimeters squared times seconds. Centimeters cubed over centimeters squared is just centimeters, so the unit would be centimeters per second, which is an appropriate unit for a velocity or a speed. And if you like, you can convert this to meters, in which case you would get 13.3 meters per second. So now we have done a short example problem using the formula for the mass flow rate.